Delaware Tech, Chemistry 100, Chemistry 110, Unit 4 continued, Nomenclature of Molecular or Covalent Compounds. Now, whenever you're writing the formula for a compound, you need to show the kind of atoms, which atoms are in the formula, and how many of each. And you can do that in a number of ways when you're naming it, but when you're writing the formula, you just write how many of each are in it. A molecular formula will show the number and kinds of atoms in a molecule. So, for instance, we have small molecules like carbon dioxide, CO2, 1 carbon, 2 oxygens. But even when we get up to something relatively simple like C6H12O6, we have 6 carbons, 12 hydrogens, and 6 oxygens. This is actually the formula for glucose, but it's also the formula for fructose and galactose and allose and mannose and literally dozens and dozens of other sugars and non-sugars. So we really have to have ways of naming compounds based on formulas that give us all the information. Here's a formula, has 17 carbons, etc. This is the formula for riboflavin, the monophosphate sodium salt of riboflavin. This is vitamin B2. By the time we're at a even medium to small size protein, human serum albumin, this is the most common protein in your blood. There are about 10,000 to 10 million, depending on how you count them, proteins or pieces of protein in your blood at any one moment. 60% of all the protein in your blood is this one protein, human serum albumin. And this molecule is a moderate-sized protein, and you might look at it and say, my God, this is huge. It has almost 3,000 carbons, almost 5,000 hydrogens, etc. But this is actually considered a medium-sized protein. And proteins can get enormous. This is actually the largest known protein, titin. It's a component of your muscles, and it has almost 170,000 carbons and almost 300,000 hydrogens, plus nitrogens and oxygens and sulfurs. So these things can get very large, and I'll tell you right now that this molecule is actually tiny compared to other molecules that have been synthesized, some of which are so large you've actually seen with your naked eye. For instance, if you've ever seen the gigantic 10-foot Uniroyal tire photos, that tire is made of rubber molecules that have been cross-linked and attached to one another. So in reality, the entire tire is one gigantic molecule. All right, so molecular compounds or covalent compounds, they're made of non-metals. You don't have metals in the covalent compounds typically, and the smallest piece of a covalent compound we call a molecule, hence the name molecular compounds. They're not held together with ions because they're not ionic compounds. They don't have pieces that are opposite charges with full charges attracting one another. So we can't name them by the ions like we do with ionic compounds. You can't use the charges to figure out how many of each atom there are. So you actually have to just tell the person how many there are. So if we have ionic compounds, we use the charges to determine how many of each there are. Somebody tells you this is the cation and you know its charge. This is the anion, you know its charge, and you figure out how many of each atom there are involved, or how many of each ion are involved. And so it's named for the ions, not for how many in ionic compounds. In covalent compounds or molecular compounds, it's exactly the opposite, and it's much easier. Here, the name tells you exactly how many of each atom. And so it has the names of the atoms in it, and it has prefixes that tell you how many of each are in the molecule. And we're going to talk about that like in the next slide. So the overall algorithm for naming them, you look at a compound, you look for a metal or hydronium ion, a metal or ammonium ion. That's the one cation, polyatomic cation, that you know about at this point. And if it has a metal or ammonium, you're going to use the ionic rules, which we've already gone over. But if it does not have a metal, we use the molecular rules or covalent rules. And that rule says you use a prefix to tell me how many of the first atom, and then you say the name of the first atom. And then you use a prefix to tell me how many of the second atom. And then you end that atom name with "ide," just like you did before with the simple anions in the ionic compounds. So let's look at an example. Before we look at an example, let's look at the prefixes. Mono, di, tri, tetra, penta. 1, 2, 3, 4, and 5. Mono means one. Di means two. Tri means three. Tricycle. Tetra means four. If you ever played the game Tetris, you know all the pieces are composed of four squares in different patterns. Pentagon has 5 sides. We also continue on with 6, 7, 8, 9, and 10. And if you remember your geometry, hexagon has 6 sides. Heptagon has 7. Octagon, which is the shape of a stop sign, has 8. Nonagon, 9. Decagon is 10. So these prefixes, hexa, hepta, octa, nona, deca, stand for 6, 7, 8, and 8, 9, and 10 in this case. So if you want some help remembering them, many diners try tarts and pies. Many mono diners die, try, tarts, tetra, pies, penta. And then from the remaining ones, hockey happens in October, November, and December. So HH, October, November, December, will help you remember these other 5 in here. So you need to remember these prefixes. So this is the overall outline for naming a binary molecular compound. So these have no ions in them. It's just 2 different kinds of atoms, and there's a certain number of each. Well, you just write the name of the 2 atoms. You put a prefix in front of each of the 2 atoms to tell me how many of each there is. And then you end the second one with "ide." And it doesn't matter that this looks like ionic compounds. They're not ionic compounds. You just name it "ide" for the second one. So for example, P2Cl5, we can see right away there's a phosphorus and there's chlorine in it. We have 2 phosphoruses, so we use the di. And we have 5 chlorines, so we use the penta. And you always end the second name with "ide," so chlorine becomes chloride. So our whole name together is diphosphorus pentachloride. And this is the basic rule for all of them, with a couple minor exceptions. The first exception, excuse me, is you never say mono for the first element. So if there's only one of the first element, you don't say mono. If there's one of the second element, you do have to say mono. And it's very important you remember that. The second exception is sometimes adding these prefixes, pentaoxide or monooxide, you're going to end up with A and O or O and O right next to each other. So instead of saying monooxide or pentaoxide, we say monoxide, pentoxide. So we just collapse the OO and the AO to just plain O. So those are the 2 exceptions. Just remember not to put mono for the first one. And for example, carbon monoxide, CO, this is the dangerous gas that can kill you, that comes out of your tailpipe of your car. Carbon monoxide, 1 C, 1 O, 1 carbon, 1 oxygen. Carbon, there's only 1, so we don't say monocarbon, we just say carbon. But there is 1 oxygen, so we do say 1 oxygen by saying monoox, and then we end it in "ide" because it's the second word. So the word carbon monoxide tells you all the rules and both of the exceptions. So here are some examples, and you can practice these as long as they are molecular compounds. So you always have to look, does it have a metal in it? Make sure it doesn't, and then you use these rules. If it does have a metal in it, you have to use the ionic rules. So the first one, I see a nitrogen and an oxygen. There are 2 nitrogens. Oh, it's dinitrogen. And there's 1 oxygen, monooxide or monoxide. So this is dinitrogen monoxide, N2O. We used to call this nitrous oxide or laughing gas. NO2, now we have 1 nitrogen. Well, we just say nitrogen. We don't say mono for the first word. And we have 2 oxides, so dioxide. So this is nitrogen dioxide, just like carbon dioxide. 2 chlorines, so it's Cl2O7. That's dichlorine heptoxide. We don't say heptaoxide. So the blending of the O and one other letter really only comes up when we're dealing with oxygen. That's the one time we're going to have an O following an A or an O following an O. CBr4. Well, we have 1 carbon, so we just say carbon. We have 4 bromines, tetrabromide, carbon tetrabromide. CO2, you already know this word. You probably didn't know where it came from. Carbon dioxide, 1 carbon, 2 oxygens. BaCl2. I'm pausing to see if you notice. Ba is a metal. That's barium. We can't use these rules. We have to go back to our old ionic rules. So this would be barium chloride. The cation is barium plus 2. Let me write that in here. Barium, get that going here. Barium plus 2. And our anion is a chloride. And therefore, that's a barium ion, and that's chloride ion. We don't have to say 2 because barium only has one choice when it's in a compound. Getting back, H2O2. Well, we have 2 hydrogens, dihydrogen, and 2 oxygens, dioxide. Dihydrogen dioxide. This one also has a common name. This is hydrogen peroxide. And this is the chemical that you can buy as a 3% solution at the drugstore and pour it on wounds to help disinfect them. The peroxide actually means 2 oxygens with 2 negative charges. We're not going to worry about that in Chem 100 or Chem 110, but if you ever hear about it, that's where it came from. But we're going to use just the IUPAC naming system here, even if it's not the common name. S2F10. So we have 2 sulfurs, disulfur. Deca is the prefix for 10, decafluoride. Don't forget the ide at the end. You don't use the ide for the first one. The ide is only in the second one, and you don't use mono in the first one ever. I4O9, tetraiodine nonoxide. Now you might notice, hey, wait a minute. I got 3 vowels in a row here. Why isn't there a rule about that? Well, it's because it's fairly easy to say. Tetraiodine. And people are used to saying it. I know the rules aren't incredibly consistent, but we do combine nona and oxide to make nonoxide. So we're only going to worry about that when it's oxygens, really. Br3O8, tribromine octoxide. So it's not octaoxide, it's octoxide. And I know that becomes a tongue twister. ClF3, and that's a Cl, that's chlorine. F3. So this would be chlorine trifluoride. This chemical is insanely dangerous. Crazy dangerous. When this people don't make this compound very often, maybe not ever nowadays. This compound can set concrete on fire. It can set asbestos on fire. It can set sand on fire. Nothing can be done to stop the fire. The only thing you can do is wait for the fire to go out. It is that dangerous. Now here's the other way around, and the other way around, this is probably the easiest nomenclature you've got, because you're literally told how many of this atom, how many of this atom, and there's your answer. Diphosphorus, oh, two P's and 5 O's. Okay, P2O5. Tetraiodine nonoxide, we actually showed this before. 4 iodines, 9 oxygens. Sulfur hexafluoride, 1 sulfur, 6 fluorines. And I'm going to leave the rest of these to you. I'm going to pause here for a second. You can practice these on your own. You'll notice the very last compound is ionic, so you have to use the ionic rules. You'll also notice that number 10, germanium, is a metalloid. Sometimes metalloids are in ionic compounds, sometimes they're in covalent compounds. Here, it's clearly written as a covalent compound rule, so you use those rules. I will tell you, if I just give you a formula with a metalloid, I will always tell you which rules to use in that case. So now, you can pause. Okay, and I'll show you the answers. And you'll notice number 5, carbon tetrahydride. The common name for this is methane. This is the active ingredient in natural gas. Most of natural gas, more than 90% of natural gas, is CH4 or methane. Methane is the correct name, but for the purposes of nomenclature, always use the IUPAC-derived nomenclature names. And with that, we'll stop.